But just as a recap from yesterday, this first section, it does go through a lot of different things or reviews a lot of different things. So yesterday we just reviewed what a function is. We talked about domain and range. We had just looked at listing out the 4 possible ways to represent a function. The warm-up you guys did yesterday, you looked at how to find function values from a graph and domain and range from a graph. And so under example 2, you're going to see that we're going to review how to find domain of a function not given a graph, given algebraically. But this first example I included because throughout this year with different types of problems as we get into the actual calculus of the class, there's going to be times where you're given a problem like this where you have to come up with an algebraic model for that situation. So this one, might be a little more challenging than the ones that you would need to practice right now, but just kind of working through how to piece this one together. There's quite a bit to this first example that I have on here. So we have a rectangular storage container with an open top, has a volume of 10 meters cubed. The length of its base is twice its width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Express the cost of materials as a function of the width of the base. So there's quite a bit of information there, and that last sentence for what you're trying to do. So this is key when you have a problem and they want you to write an algebraic model, and they tell you write this quantity as a function of this other quantity. So we want our dependent variable. They're always going to say it's the dependent variable as a function of the independent. So cost of materials is going to be our dependent variable. I could call cost of materials, say I call that C, or if you still wanted to just use Y and X, that would be fine. And then, so cost is a function of the width of the base. So I'll just call the width of the base W. So in the end, I should have C equals something only with W. So if I go back, we're talking about a rectangular storage container with an open top, and they give us its volume. So I find it helpful when appropriate to just kind of make a sketch. And in this case, I would sketch a rectangular storage container, rectangular box. Just for labeling purposes, I can label my length, width, and height of that box. Do my best to draw a 3-dimensional object this morning. And then the top is open. That will matter in terms of writing the cost function. It does not make a difference when it gives us the volume there. But because I had already decided I was going to call the width of the base W, I'm just going to label that width W. And then I'm going to go back to, actually, I'm just writing down the information I'm given. So I know the volume is 10 meters cubed. So I'll just make a note to myself, volume is 10 meters cubed here. It does give us in that second sentence, the length of its base is twice its width. So because I'm calling the width W, I can call the length of the base 2W. And then it starts talking about material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. So it doesn't say anything about the height in relation to the width. So I'm going to label the height just as its own variable. So I'm going to call the height H. So we can't assume it's the same as the width or the same as the length. It doesn't give us any relationship, so we have to use a different variable for that right now. So I'm going to now set up a cost function for this rectangular storage container. So first of all, if they're talking about material for the base or material for the sides, what type of equation are we trying to write in relation to this box? And what I mean by that is we're given volume, but do we want area, surface area? Do we want to write an equation for volume? If they're talking about material to make something, what are they talking about? The surface area. So we need to come up with a surface area equation, and then we can apply the actual costs of the different parts of that box to our surface area. Because notice it does say $10 per square meter. So we would need to know the square meters, the area of the base, and then just multiply that by 10 to get the cost of the base. So I'm going to put this together in pieces. So I'm going to say area of base. Yes, I could put equals here. So if I see that my base, my length is 2W, my width is W, so I would have 2W times W, length times width, or I could write that as 2W squared is the area of the base. And then I'm also going to, off to the side here, then if the area is 2W squared, I can put cost of the base would just be that area multiplied by $10, just multiplied by 10. So the cost of the base is 10 times 2W squared, so 20W squared. So that's one term for my cost function. Eventually, I'm going to have 20W squared plus the cost of the sides. Now, if this didn't say that the top was open, if it had a top, then we would double this, because we would obviously have two bases. So questions on that? Kind of piecing this together. There's a lot to piece together in this one example. I chose to go through this one with you guys for a reason. And then we have the sides. Do all four sides have the same area? No. So I'm still going to put area of sides and just not equals here because I'm going to have two different areas that I'm working with. So if I look at this front side, which would be the same as the back side, I would have an area of 2W times H. But I do have two of those. So I would have 2 times 2W times H. So 4WH would be the area of two of the sides. And then based on how I drew this, the sides that are on the side, if you want to think of it that way, those would have an area of W times H. And I have two of them. So 2 times W times H, or just 2WH. So I will be able to, put these together so that the area of all four sides then is 6WH. All right, and then I'm going to put together the cost of the sides. And it did say in the problem, material for the sides costs $6 per square meter. So I would have $6 multiplied by, and I can combine these, 6WH. So the sides would cost 36WH. Okay, and that means I can write an equation for the total cost. Since that is my goal anyway, I'm trying to get a cost function. So right now, this is what my total cost looks like. I'm going to call that C. C is equal to 20W squared, the cost of the base, plus 36WH, the cost of the sides. We are not done. What is the issue? What do you mean it's not simplified? Do you mean like factor it? Okay, we could factor it. You don't have to factor it. So this is going to be a conversation too that we have a lot in calculus. It is not a requirement that you simplify everything. So the reason being is simplifying is algebra, and you're tested, I'm talking AP test, you're tested on calculus. However, I am still going to show you when we go through problems throughout the year how to simplify things, or rather remind you, review with you how to simplify, because when you're working through multiple choice questions, all of those answers will be in simplest form. So you will have to know how to simplify, but when you are doing a free response question, if you don't simplify your answer, they won't mark it wrong if the simplifying was just algebra, because they're not testing you on algebra, they're testing you on calculus. So that is the conversation we will have. So we could factor this, we don't have to. Maria? Yeah, so ideally up here, we want cost as a function of the width. So we want C of W. So we can't do that yet because of Ben.
Since you know volume, you can replace H with W.
Yes, the issue right now is H. Okay, we do not have a cost as a function of W, the width, because right now cost is being represented by width and height. We need to get rid of the H or eliminate the H. As I said, everything we're going through in this first chapter, we use in different parts of our calculus later on. So these types of setups, expressing functions like this, having to eliminate variables by making substitutions, this does come up. Otherwise, I wouldn't be spending time to review it. So as Ben said, we have the volume. We know the volume is 10. So anytime you have to eliminate a variable or replace it with something, you need some other relationship that the problem gives you that you could use to make a substitution. So we can express the volume of our container with our variables W and H. So volume would be length times width times height. So I would have 2W times W times H, and that should equal the volume, which is 10. So if I just simplify that, 2W squared times H is equal to 10. But then this allows me to solve this equation for H, so that I have H in terms of W, and I can substitute that in. So here I'm going to, oops, not how you spell solve for H. Meaning to solve for H, I would have to divide by 2W squared. So H is equal to, now like I said, it's not a requirement that you simplify if you're working through a problem on your own. So I can simplify this. You wouldn't have to, I'm going to. I can do the 10 divided by 2, so that would be 5 over W squared. The W squared would still be in the denominator. And now this can get substituted in here. So now I would be able to write, rather than just C, I'd be able to write it as C of W crossed as a function of width, because my only variable is going to be W. So I would have 20W squared plus 36W multiplied by 5 over W squared. Now again, I know this is simplifying. You would be able to simplify this. I can multiply the 36 and the 5. I could cancel out this W with one of them in the denominator, so I just have a W in the denominator. So C of W is 20w squared plus 36 times 5 is 180 over w. All right, quite a few steps there. Any questions on that one? All right, you are going to see in calculus a lot of, there's a lot of algebra. I'd say most of the math we do when we do processes is algebra, the ideas behind them, that's the calculus. You'll see a lot of geometry come up. But I do want to assure you, and I'll say this throughout the year too, it's not expected that you have, like when you think back to geometry, all the formulas that you learned, it's not expected on the AP test that you have all of those memorized. So, basic ones like area of a rectangle, area of a circle, you should know those. But if they want you to do something with the surface area of a sphere, some of you might have that memorized. Most of those equations, though, they do give you in the problem. So, even I've seen problems where they're talking about surface area, but they still give you a formula to use. So we review how to come up with them, but there aren't, aside from the basic ones, it's not expected that you have those memorized. All right, so then last thing, domain of a function, and I realize for option C and D, I didn't actually write these as functions. That was poorly done on my part. We'll call this one p of x, or if you just want to call them both f of x, it doesn't matter, but I should have included function notation, not just expressions there. Okay, I also want to review something that hopefully getting through algebra 2 and then pre-calc, you're becoming more familiar with this, but you want to be able to look at an equation or an algebraic representation of a function and be able to say what type of function that is. So if we look at A, we have f of x is equal to 2x minus 1. What type of function is this? This is linear, yes, in the form mx plus b. We are in section 1.2, we do review all of the function models that you'll need to know, what their basic formulas are, what their graphs look like. So we do review all of those. If you are finding the domain of a linear function, what is the domain of a linear function? All real numbers. So yes, you can just do the all real number, the R, the set for that. You could put, this would be a way to write it if you wanted to write that the domain is all x values such that x is an element of the real numbers. Or I'd say in calculus interval notation that we reviewed yesterday is more common than set notation. So yeah, it's parentheses, just negative infinity to positive infinity, both with parentheses. So just 3 different ways you can write it. I'll accept either one. You'll probably see when the notation is given to you, you'll see the interval notation most often. For part B, g of x is x squared. What type of function is that? Quadratic. Whenever the highest exponent is 2, it is quadratic. What domain do quadratic functions have? It is all real numbers. I think you guys are thinking of the range of a quadratic. The range of a quadratic is restricted depending on where the vertex is and which way it opens. Domain though is all real numbers. That isn't a function. That's not, yes. Yeah, so you might see a sideways parabola, but it'd be represented with two functions actually, like each half would be its own function. All right, for C. Square root of x plus 2, I called it h of x. So that would be a root function. There's a square root in it. How do you find the domain of this function? Anyone remember? Grace? Yep. Yes. Yep. Any of these three ways you can express it. I just wrote the one. Yeah. Anyone remember for a square root what you have to do? Oh yeah, you know what it looks like. Yeah. It is negative 2. How did you get that? Okay, so you thought of the transformation. Okay, so here's what Kyle's thinking of, because you can think of this graphically. He's thinking of transformations, which is another thing we're going to review in this chapter. So normally, if you just had square root of x, it would start at 0 and looks like this. I'm just dotting it because we would be moving it. So this would just be y equals square root of x. This plus 2 then shifts it to the left. So now it starts at negative 2 and has that same shape. So then he reasons the domain would be, it's normally 0 to infinity. Now it's going to be negative 2 to infinity. Rather than, or if you don't want to have to kind of think of that graphically to come up with it, or when you get to more complicated functions that involve square roots, the way, because I tend to work through things algebraically, that's just my personal preference. So you know that when you have a square root, whatever is inside of the square root has to be 0 or higher. It can't be negative. So I could say what's in the square root, x plus 2, that must be greater than or equal to 0. So whatever's in the root of the radicand has to be 0 or positive. And then just solve this for x. I subtract 2, x must be greater than or equal to negative 2, which is the same thing as saying the domain is negative 2 to infinity. Okay, so a couple of ways to think through that. So here's how I could write it. If you just had this, again, for me, it's fine. This isn't very, formal notation. So you could put that into set builder and say all x values. And I will say x is always, or the domain, I'll just say x. X is always assumed to be part of the real numbers. We do not deal with any imaginary numbers in calculus. We do nothing with I. If you get to a point where you're going to get an imaginary solution, you just put no solution, no real solution. So it is assumed to be part of the real numbers. So x such that x is greater than or equal to negative 2. Or you could write that in the integral notation. The negative 2 is included, so it would have a bracket. Negative 2 to infinity. Infinity always has parentheses with it. It's not included. All right, and then the last one. Anybody remember what this type of function would be called? Starts with an R. Nope. This would be radical. A root function is a radical. It does start with an R. Yeah. A rational function is when you have a ratio of polynomials, again, we talk about this in the next section. So this is a very quick review of the types of functions. You're not expected to say what type of function you're working with on the practice that's listed there. They don't ask you that. I'm just going through it with you. So it is more formally reviewed with you guys. But because we have a polynomial in the denominator and 1 on the top is also considered a polynomial, then it's rational. Do you remember how to find domains of rational functions?
Yeah.
So remember, when you're finding domain, you're finding where the function exists or for what values the function exists. So if you have a fraction, where does a fraction not exist? Or what makes a fraction undefined? When the denominator is 0. So I'm going to take the denominator and say x squared minus x can't equal 0, and then just solve it for x. And that gives me what x cannot be. So how do I solve that for x? Well, I could use guess and check. That's an option. What type of equation is this? Quadratic equation. How do you solve a quadratic equation? What the diamond thing, what is that called though? That's not called the diamond thing. What are you doing when you use the diamond? Factoring. Thank you. So you could factor, or I heard somebody say quadratic formula. You could use quadratic formula. If you really wanted to, you could complete the square also. I would factor this personally. So there's only 2 terms. Look for a greatest common factor. They have an x in common. So I could factor out an x. I'd be left with x minus 1. And the reason we factor or can use factoring to solve is now we can set each factor equal to 0 to solve. So this means x is a factor, so x cannot equal 0. X minus 1 also cannot equal 0, so x cannot equal 1. So x cannot equal 0, cannot equal 1, but can equal everything else. So how you could write this more formally is, I could say, all x values such that x doesn't equal 0, x doesn't equal 1. So just kind of putting the set builder notation with that information. That's one way to write it. I'm going to write down here, I'm just running out of some room, the interval notation. The interval notation for this, you actually need 3 intervals. Okay, because you have to include everything but these 2 numbers. So anything less than 0 is okay. So that would be the interval from negative infinity up to 0. I can't include 0, so it gets a parenthesis. And then I have to use that union symbol, so it just looks like the U. That's kind of the representation of OR. I can also include any number that's in between 0 and 1. So I would have the next interval, I'd start with a parenthesis, and I would go from 0 to 1 with another parenthesis. So I'm not including 0 or 1, but I'm including every single number in between. And then I have another union symbol. I can include everything greater than 1. So again, parenthesis, everything from 1 to positive infinity. So that gets a little messier, but it's good for you to understand how to write that notation, or if you see it, you know what it means. Okay, questions on that? Okay, so I did put on here, I know I heard some people mention the vertical line test anyway when we were talking about functions. So just remember, if you have a graph, the vertical line test will tell you if the graph is the graph of a function or not. So if a vertical line just passes through the graph one time, it is a function. If it passes through at any point